So this will be a 3-day lecture slash workshop series on panel data, causal inference with panel data, per discussion with Jacob. This, as many of you may know, this field is developing very, very quickly. Almost every week there's a new paper. I always joke with my students that the speed that we read papers is not fast enough, and not as fast as people write papers. So it's really challenging to be in this field, but also very exciting because we are seeing much progress has been made during the past few years, only a few years. And people's thinking are start to converging, as you will see. And in this 3-day lecture series, I will try to basically give you an overview of the literature and a little bit biased overview of the literature because I also do some work in this field. So because I'm more familiar with my own work, I will spend disproportionately more time on my own work compared to the vast majority of outstanding research in the literature. But I'll try to give you an overview, give you an idea of what literature is studying. And I believe some of you are methodologists, and this is a, I think, very both competitive and very exciting place to work on and working. Okay, so I'll try to use my iPad, so sometimes there will be a lag. Please stop me either by waving your hands or raise your hand, or virtually, or just shout. I'll just stop because sometimes it's kind of hard for me to follow the Q&A. All right, so let's move on. The motivation is actually very simple. We don't have a lot of luxury to conduct experiments which are sought as gold standard in causal inference. Right? It's not very easy to do experiments, and RDs are difficult to find, and IVs are problematic. I recently did a literature review on IV. It's very hard to find good IVs. So what we end up with, we have a toolkit for causal inference, right? There are not many tools inside. So we often end up with panel data. Panel data come to the rescue for causal inference purposes. And if you write a paper and you don't have an IV, you don't have an RD, you're not running experiment, oftentimes you say, I use panel data and leverage on both time and unit dimension to try to make closer to a causal argument. And sometimes people buy it, right? So that's the main motivation why we study causal inference with panel data. And it's not surprising that in our field, in political science, there are many papers published using panel methods, most commonly difference in difference methods and two-way fixed value models. During this 3-day workshop, I will use DID to denote the difference in differences, and 2WFE to denote two-way fixed effects. And note that when you write papers, difference in differences, there's always a plural in the second difference, right? Because it's literally a difference in the multiple differences. Sometimes when I review paper, I don't see the plural. It's actually wrong because it's literally, the name is literal for the method. But these two methods are the bread and butter in causal inference with panel data, at least in our discipline, also in economics and other social sciences, I believe. And they, of course, they have benefits. They're so popular, there must be some reason. One is the most obvious reason that they account for fixed effects, unit and time heterogeneity. Right? This is what we were taught in grad school. If you're worried about individual or unit level heterogeneity, or if you worry about common time shock, you can use fixed effects to address them. This is of course true. And you can accommodate many types of data structure, of course, continuous variable, binary treatment, and treatment with reversals, everything. Well, two-way fixed effect is simply an estimator, right? An estimator is very close to a ORS estimator. It's a machine. It does not guarantee what you get out of the machine has causal interpretation, but it can run with a lot of types of data. And that's also one of the reasons why people like this method so much, because you don't have to change a machine, change a tool when you are using a different type of data. And also it's very easy to estimate and interpret with improved algorithm like LFE in R or RAC-HDFE in Stata. Both are using a so-called MAP algorithm to partial out the fixed effects iteratively. I think a lot of how the fixed effects are run is not what we learned from textbooks, because most of the data we use are unbalanced. Using textbook demeaning methods, you cannot very quickly get the fixed effects estimates, and you cannot by adding dummies because the matrix will be too wide. So people are using the so-called MAP algorithm to do that, and it's getting very, very fast, especially with well-maintained packages like LFE or RAC-HDFE. It's also very easy to interpret because it's a regression method. With some assumptions, you can interpret beta coefficient as the treatment effect or something close to average treatment effect. But we know there will be problems with that. And recently, there are a lot of reflections and discussion, especially in the econ literature, on fixed effects. So one of the discussions is on the assumption. What does the strict exogeneity assumption actually imply? We have now better understanding of this problem. We will discuss this in today's lecture. Another discussion, very vivid discussion, set of discussions is on treatment effect heterogeneity. People start to realize that DID and two fixed effects are quite different machineries, although well, they're closely linked. If you are an economist, you always, most economists equate two fixed effect with DID, right? Probably because the famous textbook by Andrew Spischke, because they interpret two fixed effects as a way to estimate effects, average effects in parallel worlds. And they use the idea of DID to motivate two fixed effects. This is right, but this is right under some conditions. And a lot of discussion in the literature are investigating the assumptions required to draw this parallel. Sorry. And so this is also this will also be one of the topics in today's discussion. And there are a lot of papers written on this, recently, very prominent high-profile papers. Any questions so far? Okay, good. All right. So what will we cover in this short workshop? First, we will discuss what's the difference between DID and two fixed effects. So after this lecture, I hope that you, in the future, when you write papers, you won't at least directly reach to the equivalence between two fixed and DID. You want to be very clear, because the reviewers will get picky when this knowledge start to propagate. DID should be reserved for, well, the most classical case is the two-period two-group. And then maybe with one treatment timing, the timing is the same, although you have multiple periods, but only has one group that receives the treatment at a fixed time, and the other group does not receive the treatment. That's the classic DID. Maybe you can generalize this to staggered adoption, which we will also explain. And then more complex design than that, especially with treatment reversal, you cannot. I would encourage you not to use DID to label them. At least it's only metaphorically it's a DID, but it's actually not DID, because DID is non-parametrical, but two effects, or at least semi-parametrical, but two fixed effects are parametric with very strong parametric assumptions. These two are not equivalent. The Card and Kruger reintroduced the idea of DID date back to John Snow, right? Those not from the popular drama, but English scholar studying malaria in England, in London actually. But when Carl Kruger first introduced DID back to social science, it was very clear. There are two states and there are two time periods, and we will discuss the difference between them. And I will also ask you to pay much more attention than we currently are doing to the identification regimes or identification assumptions. What do I mean? I mean, basically it means what we think the treatments are assigned. When we use panel data methods, oftentimes we have a structural model, we have an outcome model. We write down YT equals to alpha I equals to cos IT plus something plus beta I XIT, beta XIT, and then we never really discuss how the treatment is assigned. Sometimes we say, oh, it's basically the strict exogeneity assumption is satisfied, but we don't spend too much time thinking about what does the assumption imply. And third question is, this is relatively well known because it's very obvious. When the assumption of parallel trends, which is required by both DID and the two fixed effects, because strict exogeneity implies parallel trends. When the parallel trend assumption does not seem to be satisfied, does not seem to work, of course, this assumption is not directly testable because this assumption involves counterfactual, and we don't observe counterfactuals. It's not directly testable, but we can look at a pre-trend, so-called pre-trend, to gauge whether this is likely to be true, right? When this is unlikely to be true, when the parallel trend is unlikely to be true, what do we do? So this problem is relatively well known, but recently there have been some solutions to addressing this. Right, and the fourth question we try to answer is how to fix the weighting problem. And first of all, what's the weighting problem with two fixed effects when the treatment effects are heterogeneous? I'm sure some of you have heard of Goodman-Bacon and a lot of negative, discussion on negative weighting. I think when you, I think in a few years, maybe sooner than that, when you start to write, when you write papers with two fixed bet, people will start to ask this question. So I think it's a good idea to know what people are talking about with negative weighting and what is the root cause for it and how to fix it if possible. Okay, so this is the what we try to answer today. Moving toward tomorrow and later, sorry, not tomorrow, moving to Wednesday and Friday, we will actually introduce more estimators. But I try to fit estimators to not only two broad identification regimes, but also link them to the questions I pose here. Any questions so far? Okay, all right. So yeah, so in the other two, on Wednesday and Friday, I will spend more time to discuss estimators, but there are so many of them. Without a proper roadmap, it's difficult for you to think about them, think about their relationships. I think the conceptual issues are more important here. Excuse me. All right, so the first question I want to ask is what's special about panel data? So we all know the fundamental problem of causal inference that we don't get to observe both versions of potential outcomes. We don't get to observe counterfactual. By the way, in this lecture series, I would mostly focus on, or almost entirely focus on the case with binary treatment. There's one reference to continuous treatment, but I won't spend much time on it. The reason is very simple. We don't even understand causal inference of panel data with binary treatment, not to mention continuous treatment. Continuous treatment is even more complicated. And people, you can think of continuous treatment as discretized as a multiple, well, a series of binary treatment. You simply discretize the continuous treatment, but things are more complicated, I think. And I think more research needs to be devoted to continuous treatment in panel data. But this lecture is mostly about binary treatment, and also such that we can use causal language more easily and notation more easily. Okay, so there are Holland in this paper, I'm sure most of you have read, proposed two solutions. One solution is what he called a statistical solution, is to make use of some kind of randomization or ignorability to leverage on information from other groups to get an idea of your counterfactual, or at least average counterfactual. That is what experiment is doing, right? You don't get to observe your own counterfactual, but in a randomized controlled trial, on average, the control group's average can serve as an estimate for the average counterfactual. Another solution is what he called the scientific solution. I actually think this is, well, I don't know whether it's a proper name. Sometimes this type of solution is very unscientific if you make a model wrong. The scientific solution is basically try to leverage a model. The model must assume some kind of homogeneity or invariance assumptions. A simple example I give here is that if your C array implies that the long-run growth rate of the US economy is 2.5, so anything deviate from that, you can attribute that deviation to either random noise or to some treatment effects. So you have a model for the dynamics or evolution of your potential outcome, and then you observe something different and you attribute the difference to some treatment. That's another solution. And many of our methods involve both solutions, because whenever we write a parametric model, we are invoking the scientific solution to some extent, because we have some prior of the data generating process. So panel data, the beauty of panel data is that it allows us to construct counterfactual, sometimes at the individual level, sometimes at the group level, using information from both the past and the others and your neighbors. If you're interested in this particular treated unit, you can use its past information to build counterfactual. You can also use its neighbors' information to make better prediction for the counterfactual. That's what's special about panel data. The difference is exactly using that idea, using your own intercept, right, the level to be your intercept, and then using your neighbor's change as the time change, and then you put these two together to make a prediction for the average counterfactual outcome for the treated group. And the caveat is that treatment assignment mechanism will be very complicated and can be very complicated. Although in special cases like two-peer or two-group DiD, it's much more simplified, but we are not always that lucky. With two fixed fact, it's actually two fixed event DiD. There are, well, a little bit confusion here. DID is both the name and a name of a design, and also a name of an estimator, right? Literally, it's a name of an estimator, but we also we also use it to represent a design. But TUI-fixed fat is mostly a estimator. It's a machine. It's a function. What design underlying TUI-fixed fat is sometimes unknown. There are papers discussing this, but it can be very, very complicated. And that's why using TUI-fixed fat model does not always guarantee that what you get out of beta is causally interpretable. It is difficult because of all kinds of SUVA violations. SUVA represents stable unit treatment value assumption. If you're unfamiliar with this term, this basically means some kind of interference or spillover. But if you think about pattern data, the problem is very severe because you not only have cross-sectional spillover, it happens all the time. You also have temporal spillover, right? Because the treatment can have effects on future outcome. Your past outcome can have some kind of influence on your future treatment assignment and all kinds of things. And when you have such complicated SUVA violations, we know that one way to address SUVA violations is basically to expand the space of the treatment, of your treatment vector. That will make things so much complicated. So if you imagine the history, the total universe of history of treatment being the expanded treatment, if that's the case, with a general data format, you will basically run out of data. You will have way too many treatment compared with the number of units. So that's a problem. I'm not sure I'm clear here, but I hope things will get clearer later. So far, do you have any questions? This is a very high level. It's very conceptual. Do you have any questions, especially our class? Okay, good. All right, so here I give you some stylized design. This is from a recent paper by Haber et al. They're discussing the popular designs studying the effects of interventions in COVID. So with panel data, you can use before and after design. So when you use a before and after design, so this is something important. Whenever we use a estimator or design, we are making assumptions. We are making assumptions of how you predict the counterfactual. Sometimes you don't realize that, but you're actually doing so, right? Let's say if you're using a before and after design or pre-post design, although sometimes we don't realize it's the case, we're actually making a assumption, a fairly strong allocation assumption, which is your past outcome will serve as the counterfactual of your future potential outcome, right? And then you take a difference between the actual outcome and your past outcome, which is now your counterfactual. You attribute the difference to the treatment effects, right? Even though when we estimate before and after, this is not entirely obvious, but if we want to interpret the coefficient before from a before and after design as causal, so we are making these kind of allocation assumptions, right? Causal inference is all about estimator plus allocation assumptions. We learned this from some causal inference class, and you must have taken because of the fundamental problem of causal inference. We have to make some allocation assumptions. Here, the allocation assumptions is that we use pre-treatment data as counterfactuals for the post-treatment data. And another example is interrupted time series. So we're essentially, well, oftentimes if you're using an interrupted time series, you're estimating the causal effect, the cutoff, the time cutoff. It's sort of like an RD in time. But well, there's some subtle difference between this and RD because usually with interrupt time series, the interval, the data interval is fixed. Every month you have a data point, every minute you have a data point. Not always, sometimes you have multiple. So the density around the cutoff is not always, cannot always increase as sample size increase. That's the sort of difference. If it can, then there's no difference, no big difference between RD and interrupted time series. But you're essentially fitting two lines or fitting two lowest curve toward the cutoff and then estimating the local effect at the cutoff. That's the interrupted time series design. Another design we're all familiar with is the difference in difference. With difference in difference that I alluded earlier, you are using the time change for your comparison group, the control group, plus the intercept from the pre-period, from the first period to serve as a counterfactual. So we're also making an assumption of how the counterfactual should be sorted out in this design. And this is a classical DID design, so there's no misuse of terminology. We have two pairs, two groups. We're using change plus intercept as our guess of the counterfactual. Why can we make such assumption? Because we believe so. It's quite as you can see, if you really think about it, the assumption is quite heroic. And why can we make such assumptions? It's an additive assumption. So it's a model with additive fixed effects, essentially. There's pretty strong assumptions embedded. Okay, so another design less popular in our discipline, but being used in economics sometimes and epidemiology sometimes, is what people call comparative interrupted time series. The difference between comparative interrupted time series and difference is that instead of using the change in level before after for your neighbor, you're using your neighbor's change in slope to make counterfactual for a treatment group. Is that clear? You're also making a you also try to make a estimate around the cutoff, around the time cutoff. But here the comparison is not that I experience the same changing level from the control, but we have the same changing slope between the treatment and the control group. Is that clear from this picture? Okay, yes, this is, when I first see this, it's a little bit counterintuitive to me, but after seeing it for a while, I get used to it. Okay, so the scientific solution, again, is about modeling. You're making some assumption. All this, for a previous case, you're using some kind of scientific approach, right? You're making a model. Before and after, you're making a model. It's not purely statistical. If it's purely statistical, it should be you're running an experiment. You use some non-parametric methods. But with all the methods that we mentioned, you have some implicit model in your mind. And all models are wrong, some are useful. And statistical solution with panel data can help us extend the conventional ignorability assumption in observational data in a cross-sectional setting to a more, I would say, more relaxed version of this assumption. But depending on how, well, sometimes you can say they're weaker assumptions because the panel data, in panel data, you have a lot of potential violations of SUBA or of application auxiliary assumptions. These are not necessarily weak, but people like panel data because they think ignorability assumption based on panel data sometimes are weaker than the ignorability assumption in cross-sectional setting. This is because your past information, a unit past information, is very predictive of its current and future potential outcome. So sometimes we think if we condition on past information, if we condition on my neighbor's change, I may be able to get closer to ignorability. That is sometimes true. I think that is, I would say, I feel much more comfortable if I see evidence showing that this is the case than simply doing some sensitivity analysis with a cross-sectional setting. In cross-sectional setting, you really, with observational data, without IB, without RD, you're really limited. You can do some bounding, you can do some sensitivity analysis, but the ignorability assumption is really hard to get around with. And panel data makes both easier because you can you have some free testing data. Let's say if you have a DID design, the pre-treatment data for the treatment group can use as testing, can use to help you build a better model. And because you have two dimensions, it's kind of easier for you compared with cross-sectional settings for you to build models. And also the additional dimension helps you to relax the conventional ignorability or SOO assumptions, selection observable assumptions. And we can do a little bit more. For example, we can take advantage of the matrix structure. With panel data, each variable is represented by a matrix, right? And if we have more than one variable, the multiple variables is a tensor. And sometimes you have multiple outcomes. It's a multi-level array or tensor. So sometimes you can leverage on this matrix structure or tensor structure to do a little bit more complicated modeling. Okay, so that's the overview. That's why we bother using panel data to do causal inference, but the devils are in the details. In the first lecture, today's lecture, I will primarily focus on DID and two-elliptic models because these are the most commonly used methods in our discipline and in social science in general. And then in lecture 2, I will discuss our first review, the synthetic control method, very quickly. I'm sure most of you have either heard of it, learned from it, learn it in your class, or use it in your research. And then it's many extensions or friends or algorithms similar to synthetic control method. Then I will talk about factor augmented methods, a factor approach for panel data, which is connected to the synthetic control method but from a different perspective. It's more model based. And in the last lecture, I will talk about the matching and reweighting method. These are non-parametric, semi-parametric methods, and then hybrid methods. Hybrid methods are methods using both matching and weighting, and also a model, sometimes a factor model, sometimes a fixed effects model. And I think for those who are methodologists, you may have heard of the term doubly robust. A doubly robust estimator, in the estimator, when either the outcome model is correct or the treatment assignment model is correct, the matching with weighting is trying to fix the treatment assignment issue. If either of these two models are correct, your estimator will be consistent. So hybrid models are these kind of doubly robust models. Okay, so this, if you look at this structure, it's more like a we're always talking about estimators or different types of algorithms. But I also want to organize this 3 lectures around designs. So if you think about it, the first thing is the DiD and TOEIC fixed effect help us to better understand the requirement, the required assumptions for these models to be causally interpretable. And then because we're limited, because these methods have limitations, for example, failure of parallel trends, we have to use alternative methods like synthetic control. Synthetic control is one way to get around failure of parallel trends. And then its extensions are better algorithm, but from a design perspective, fairly similar. So lecture 2 are algorithm similar to synthetic control, but from a design perspective, similar. And I would argue that the factor augmented models are also having similar annotation assumptions as to synthetic control. But then the matching and weighting are actually slightly more interesting, because they can work with the assumptions, similar assumptions for synthetic control, but they can also operate under a different set of assumptions, what we call sequential ignorability. So I will, in the syllabus, I talk about there are 2 main application regimes. One is based on strict exogeneity. Another is based on sequential ignorability. I want you to remember this because it's gonna come up again. Okay, so today first I will discuss DiD very quickly. You will feel bored because you're so familiar with it. And then the 2 fixed effect assumptions, and then the weighting problem. I think behind this set of slides, there may be 4 or 5 papers that basically organize materials from 4 or 5 newly merged papers and try to make sense of them. Okay, so quick review of DiD. Here, DiD literally means 2 groups, 2 periods. We have 2 group treatment control and 2 period T and T apostrophe. And the timing is fixed. So the treatment group get treated at the 2nd period. So the DiD, with DiD, you have a functional form assumption. I'll explain why. So you basically can write your outcome, your realized outcome YIT as a summation of the, sorry, I actually have a pen. Oh, I forgot. Sorry. I actually have a pen, high tech. So this part is different from TOEIC fixed effects because it's non-parametric, right? You can allow the treatment effect to be individual treatment effect. It can be arbitrarily heterogeneous across unit and over time. Although you're not individually identifying tau IT, you're identifying the average of tau IT, the ATT, but you allow the individualistic, in the literature they call individualistic treatment effect to be arbitrarily heterogeneous. And then you have this additive fixed effects, individual fixed effect and time fixed effect, common time shocks. As I said, any panel models, with any panel data models, you're implicitly making assumption of how you want to predict the counterfactual. So here with DiD, you're essentially making prediction for a counterfactual with 2 additive fixed effects and then a random error in this equation. And the difference between, this 0 should be 0. So the difference between Y1 and Y0 is tau IT, which can be arbitrarily heterogeneous. Okay, and the parallel trend assumption is the difference between, it's about the non-treated potential outcome, Y0, YT0. There the change is the same between, the average change is the same, sorry, the average change is the same, is a mean independence assumption, right? It's not about the individual. So on average, the changing level is the same for the non-treated potential outcome. It does not make assumption for Y1, it makes assumption for Y0. Or equivalently, if you write it out, it's essentially these 2 sets of errors to be the same with the modeling assumption. So you can, so what does that mean? It means basically, if you have this model, and then on top of that, you have this assumption on the error terms, you can get parallel trends as well. so the parallel trend, so when we talk about parallel trend, we always talk about this one. And it looks like a weak assumption, but in order for this assumption to be true, you actually are implicitly making a functional form assumption. That is what I meant. And this for difference in difference to work, or for parallel trends to be satisfied, this model is scale dependent. It's not scale independent. It's scale dependent. Meaning, if you transform your outcome data to a log YIT, this assumption most likely will not be satisfied. Right? We have I think some of you must have this experience. This parallel trend seems to work with one transformation of the data, and then with another transformation data, it doesn't work. With log Y, it may work. With the level Y, it does not work. Right? So parallel DID is not scale independent, not like experiments. Experiments are scale independent, right? Okay, and our estimate is ATT. We care about the average tau IT, average treatment effect for those who are treated, and that is why because we care about ATT, we make assumptions for the Y0 in the parallel trend assumption, and it can be non-parametrically identified when you only have two periods and two groups, because essentially it's a difference of 4 cells. Right? So we write it this way, and what we don't get to observe is the treatment group in the post-treatment period. So here in this matrix, I subset the matrix into 4. Partition this matrix into 4 smaller matrices. So we have the treatment group, the first row, and then the control group in the second row, and then the first column pre-data, and second column the post-data. What we are literally doing is trying to use the average of these 3 small matrices, or these 3 cells, to make a prediction for the average Y, the average potential outcome in the top right cell. That's literally what difference in difference does. Okay, there are some threats to difference in difference. Oh, sorry. So here we essentially look at it, what's the difference, right? That we used post minus pre, and then we put this difference on top of the intercept. And then, of course, we take in the expectation. Everything is the expectation. That will be the counterfactual for this period. And then we take a difference between the counterfactual, average counterfactual, and the average actual realized outcome. That will be our difference in difference estimate. And there are some threats to DID. Again, from this Harvard paper. On the left, it is when the parallel trend assumption is satisfied. Again, this assumption is not testable, especially with 2 pairs of data. It's not, because it involves counterfactual. So the first violation is basically you have divergent trends, right? So this is one trend, it is another trend. Because you don't get to observe more pairs of data, it's impossible for you to evaluate whether you have parallel trends or divergent trends. So basically, this dotted line represents the true counterfactual for the treated group, for the average treated group. But what you assume is this dashed line. So that is certainly different from the actual counterfactual, and that's why you make your estimate is biased. Is that clear? Okay. So another possible error is because as I said earlier, DID is scale dependent. Maybe you have there is some scale difference. Maybe originally the logged version of Y follows the parallel trend assumption, but the level term does not. So when that does not, it grows exponentially. Then the counterfactual does not follow parallel trend. That's this case. Okay. And the third violation is you misplace the timing of the treatment. So you make an error on so the treatment actually happens 1 period or 2 periods later, but you attribute to 1 period earlier. So you also make a mistake. A fourth violation, possible violation, is you have a bundle of treatment. You have a lot of shocks at the same time that each of them can affect the path of the counterfactual path. But you attribute the difference to this particular treatment you're interested in. Let's say you have some COVID restriction. You have a lot of them. You have mask wearing, you have mobility restrictions. They're happening at the same time. But if you don't, they're highly collinear as well. So it's very difficult to separate them. And you just throw in a dummy estimate effect, the estimates may be misleading. These are the potential threat to DID design. Okay, so so far the DID design is all 2 pairs, 2 groups. But what about more than 2 pairs? So in a classical more than over 2 pairs DID, I still accept it to be DID. Is basically something like this. You have multiple peers. I would use this type of plots a lot. This is what I call the treatment status plot. It's very helpful when you before you run independent data models. I strongly recommend you to at least make such graphs once before you run a model, because you give you a sense of how the treatment is assigned and where the variation comes from. So in this particular design, the x-axis represents time, the y-axis is unit, and the treatment is dark blue, and the control is light blue. And what the idea is trying to do is try to make an estimation of the average potential outcome, right, under the treatment. So this is what we want to estimate, and then we use information from all these cells to make such an estimation with DiD. The DiD is a very simple algorithm, as I just mentioned. But this, you can call this a DiD, although it has multiple periods, but because the timing is fixed at period 15. Right, so another potential extension is what researchers call staggered adoption. So for these 4 units, they adopt the treatment at period 21. For these 4, they adopt at period 24. And then once they take the treatment never reverts back. This is what they call the staggered adoption. You can also call this a DiD because it's very easy to find, to show that this is actually a weighted average of multiple smaller DiDs, because for these groups, you can always use the control as your comparison group. But if you only care about the treatment effects up to 3 periods after you get a treatment, for the first cohort, for the cohort that gets the treatment the earliest, you can use the rest of the units as your control, right? If you only care about treatment effects up to period 3, and for these guys as well, for this cohort as well, you can always use this group of units as your control if you only care about average treatment effects on the treated up to 3 periods after getting treated. Of course, the period control is always there. It helps you to gauge the treatment effects for a longer period of time. So staggered adoption is a direct extension to DiD because you can decompose it very easily into multiple smaller DiDs. Okay, and again, whatever method you're using, you're actually making an assumption about how the counterfactual should be constructed, or at least the average counterfactual should be constructed for those under treatment condition. Fixed effect is doing similar things, although as you will see, under a much stronger assumption. DiD under less stronger assumption, and the DiD only assumes the 2 additive fixed effects. It does not assume the effect to be constant. Okay. All right. So, so far, what we talk about is the outcome model. Oh, Louis, yes.
Hi, sorry, just a really quick clarification question here. So for the staggered adoption case, is the assumption, the parallel assumption, needs to be held for every cohort or just the average? So we have 5 cohort being treated,
right?
And do we have a stronger parallel assumption here compared to the 2?
It's a great question. So first of all, when people estimate using this type of data to do estimation, they normally use 2 fixed effects, right? And using 2 fixed effects, they assume, at least when they write papers, they assume strict exogeneity. And with strict exogeneity, the assumption you just mentioned is satisfied. So any kind of parallel trend is satisfied under strict exogeneity because it's very strict. So you can, it's the multiple parallel trend assumption between each of the cohort. They call this the cohort. They call the group of units that receive the treatment at the same period, the cohort. In the literature, in the panel literature, they call this average cohort treatment effect for each group that received treatment at the same time. So there is a implicit parallel trend assumption for each comparison, for any comparison between 2 pairs of cohort, right? You can compare this cohort with this cohort, this cohort with this cohort, and this cohort with the pure control cohort, right? And with strict exogeneity, the parallel trends for any such comparisons is satisfied because it's the strict exogeneity is a very strong assumption. Does that make sense? But as we will discuss right away, on the design perspective, so we're exactly trying to tackle this question: how should we think about the treatment assignment mechanism under such a design, right? So it's strange for us not to think about treatment assignment with panel data if we think we're making causal inference, because in any other scenarios with other type of data, with cross-sectional data, we always ask ourselves and always get asked by reviewers, right, what is your treatment assignment mechanism, right? But why don't we ask this question ourselves, to ourselves, what is our treatment assignment mechanism with panel data? That is strange, and that is what people are working on recently. Okay, so let's move on. All right, so next. So I give you two possible designs for DID, and so the next question is, how is the treatment assigned, right? It can possibly be assigned if you see treatment status like this. AC and Sudan AC and Guido Invens has a paper a few years ago on DID from a design perspective. In that paper, they cover both the classical DID, classical multiple peer DID, and also staggered adoption. So when I read papers or review papers, people say generalized difference in difference. I really don't know what people mean. Normally, if I read between the lines, it's basically any fixed fast models. It's called generalized DID. But now, I'm at least myself, I'm more cautious when using this language. And so in this paper, it covers the one fixed timing and staggered adoption. It's a pretty good paper because it gives you an idea of how to conceptually think about treatment assignment. Okay, so we have n units and t periods. And then the treatment timing. So here, timing is the assignment. You're rolling a die. On each face of the die is a time, right? So you can get treated in the first period. You can get treated in the second period. You can get treated in the eighth period. Get treated at the last period. You can never get treated, which is represented by this infinity sign. This infinity sign does not literally mean infinity. It basically means it's outside. The timing of your getting treated is outside the observed time window. So you're assigned one face of a die, and this number on the die tells you when you get treated. And once you get treated, you stay treated because it's staggered adoption, right? The classical DID is also staggered adoption. Once you get treated at time t0 plus 1, you always get treated. So this simplifies our thinking. And the treatment assignment for each unit I, you basically draw one number from the set of all potential treatment timing. This basically determines for each unit, you have t plus 1 treatment status. And this t plus 1 treatment status define t plus 1 path for the counterfactual. Right, so you have, sorry, no, I shouldn't say counterfactual, I should say potential outcomes. You have for each unit, you have t plus 1 potential outcome history. Does that make sense? So you have maybe this line is you never get treated. If you get treated time t plus 1, maybe your line is something like this. If you get treated at time t plus time period 10, maybe it's something like this. So you have t plus 1 pass as your potential outcome. Okay, so this is y and this is time. This is y. Okay, so the treatment vector is entirely determined by this AI. So if you know AI, you know DI. DI is a vector because if AI is any of these periods, you have AI minus, sorry, this should be, I think it's a misnotation. It should be a small a, because AI is a random variable. The AI is the value. So you can understand sort of if AI equals to A, let's say, let's not use AI equals to A. So you have A minus 1 zeros. And then after the A period, so starting from the eighth period, you always get treated. So the vector DI is determined by AI. So the realized outcome is YIT with this number AI. This is the treatment, your treatment. And then all your potential outcome is you have T possibility of AI, T plus 1 possibility of AI. And the average causal effect, this is a bit fairly complicated notation. The average causal effect at time T, this is basically the potential outcome time T. And these two represents your comparison. But when we talk about treatment effects, always one treatment compared with another treatment, right? One condition compared with another condition. So A represents your potential outcome pass when you get treated at time A, and infinity means you never get treated, right? That's the comparison of two paths, okay? And then this path, well, this is a, let's say this is the infinity line. and then this is the line when you get treated at time A, and then this is time t. This is time t. So this part is tau t infinity A. Right? Is that clear? Okay. So we're comparing pass with pass. Of course, this is impossible, right? Because I only get to observe one pass for each unit. Right. So I have to rely on some statistical solution, some assumptions, allocation assumptions kick in, right? Such that we can use each other's information to serve as one another's counterfactual pass. So if I'm actually getting treated, so my this pass is observed, but you don't get to observe this infinity pass, this never treated pass. You probably want to use your neighbor's pass as your counterfactual, some version of your neighbor's pass if your neighbor is never treated. Okay, that's the idea. Okay, so that clarifies a lot of things. When I read this paper, it's not a difficult paper from a mathematical point of view, but conceptually it's very helpful because it helps me to think how the treatment is assigned in a DID design. Essentially, if in a two group DID design, two group multiple pairs DID design, you're rolling a die to determine who's getting into the treatment, who get treated at time t0 plus 1, and who never get treated. Right, that's the classical DID design. With staggered adoption, you're rolling a die to determine who gets treated at what time or never get treated. So that's the hypothetical experiment you're running in your mind. And then with that understanding, you can derive estimators and under some assumptions to make your estimator consistent for your estimate, which is defined here. Okay, here, can someone tell me why the staggered adoption assumption is very helpful? The staggered adoption meaning that you get treated, you never reverse back. Your treatment status always stays at 1. Why that assumption is helpful? Can some of you tell me? Well, I'm asking why do we need a staggered adoption assumption? Why do we limit our focus to designs with staggered adoption? Once you get treated, you never get. Yeah, exactly. So there's one person in the audience. The number of potential outcomes dramatically decrease, right? You only have t plus 1 treatment history, and you're making comparisons between potential outcomes, right? So you only have, although we are living in a panel data world, you have a lot of combination, 2 to the power of t, right? 2 to the power of t possible combination of treatment history. But with staggered adoption, the number of treatment history reduced to t plus 1. And then when n is relatively big, you can make reasonable comparisons between different treatment histories. You can allow a lot of large numbers of treatment theorem to kick in because for each cohort, you have enough data. Does that make sense? If you allow, so with fixed effects, if you allow treatment reversal, you have to rely on a lot of additional parametric assumptions or homogeneity assumptions to be able to take advantage of data to estimate any treatment effects. That's because your units, the number of units will always be smaller than the number of treatment history. Okay, so you cannot make non-parametric comparisons, make non-parametric estimations of treatment effects between 2 different treatment history. Does that make sense? Okay, good. All right, so possible assumptions. Possible assumptions, not so. In this paper, Susan and Hiddo, they explore possible assumptions, but then they're not saying these assumptions are necessary. They're saying if I have this assumption is sufficient for me to derive some results, to get to arrive at some results. Okay, I want to be very clear. This is not necessary assumptions. These assumptions are not need to be made. Do not need to be made in each design, but these are the possibilities. So if you have random assignment of A, of course, this is very strong, right? This is experiment essentially. You're running experiment with a time dimension. So some of the units you roll out the experiment early, other units are late adopters, and then you can use the time gap. That is not uncommon because if you work with a partner, with NGO partner, for example, and they, at the end of the day, for ethical reasons, they want to roll out to every village that they're working, but then you may be able to convince them to start early in one side of the village and then to roll out the treatment later in the rest of the village. So that is possible, and that is a DID, right? That's in treatment assignment. You can understand this as a DID. The treatment status distribution will be like a DID, and no anticipation. No anticipation means that I know the treatment is going to come at time A, and before time A, the 2 paths. Let me actually illustrate. So this is when my treatment. So I was assigned to treatment time A. So I will get treated at time A. So if my, so I have two paths. One is this red one, which is the infinity path, and another path is maybe this one. This is basically saying for any time t smaller than A, so my YIT and these two potential outcomes are the same. There's no anticipation, right? If this is basically a potential outcome Y under A, if you have assumption like this, before A is already divergent, so you have anticipation, right? That is not satisfied. And this assumption is I think a reasonable one, but can be violated by data. Okay, if you anticipate a policy is going to affect you, people adapt to that future policy change and potential outcome change. Okay, and sorry, and the next one is invariance to history. This is to say this is the other side of the non-anticipation, but it's much stronger. This is to say you have you have infinity. Let's say so. This is YA, and then there's another one B, using another color. Right. Once you get treated, past the treatment, until my level is the same. Past the treatment, my level is the same. Yeah, at time t. So this satisfies this invariance to history. This is a very strong assumption. This essentially rules out the treatment dynamics for different assignment of A. But this assumption is required by fixed effects. Two fixed effects. And the strongest is the constant treatment effect over there are two. There's one is constant treatment effect over units, and then one constant treatment effect over time. And fixed effects require all of these, right? Okay. So in the paper, they spend a lot of time discussing what kind of quantities can be identified under different sets of assumptions, a combination of assumptions. In particular, under random assignment, first of all, randomization inference can be used. This is very handy, right? You don't even need to rely on any asymptotic theory. You can get exact inference because treatment is randomly assigned. And two fixed effect is unbiased is unbiased with random assignment. Even these assumptions are not correct. It gets you a weighted average of causal effects. But this rarely is the case. Random assignment is almost impossible with observational data. Okay, so next we ask the question when the parallel trend assumption is more defensible from a invariance point of view, a scale independent point of view. This paper, it's also, I think, an important conceptual paper. Well, the paper is not conceptual, but raises a conceptual point. When is parallel trend assumption scale independent? So acknowledge that parallel trend assumption is scale dependent, and it asks when is it not the case. So basically, when is assumption not sensitive to strictly monotonic transformation of the outcome, like the taking a log or taking a square root, and in which condition the parallel trend assumption still hold if you conduct a strictly monotonic transformation of the outcome. How can I get a guess? Can you give me intuitively under what conditions? Oh, you have the slides. So, any of you can have a guess without looking at the slides. So the question is, you have a parallel trend assumption, right? And it works for one version of Y, one particular transformation of Y. And if I conduct a strictly monotonic transformation, and the parallel trend assumption still hold. So when that is the case. So what kind of sufficient assumption do we need? Random assignment, right? Random assignment is one. If you under random assignment, parallel trend is always satisfied, right? Because the treatment control the distribution of treatment paths and control paths are exactly the same because of random assignment. So they're always parallel. They're not only parallel, they're identical to each other, right? Does that make sense? So here we talk about the design. So here treatment assignment happens across units. We're rolling a die. Some get treated, some get untreated, right? If this die is randomized, and by randomization, the distribution of the potential outcome paths will be the same across treatment control groups. So the parallel trends for sure will be satisfied. Not only parallel trends, but identical trends. On average, the trend will be identical because of random assignment, right? That's not difficult to understand. A stronger parallel trend assumption is actually slightly weaker than random assignment. It requires a version of parallel trends on the distribution, on the entire distribution of the paths of Y0, of potential outcome 0. Okay, so it holds when population consists of two groups. One subgroup is that when the treatment is as if randomly assigned. That is what I just explained. Another subgroup is when the distribution of Y0 is stable, right? It's basically stay flat, right? And if you have a randomly assigned group, subgroup, and then you have a fixed group, and you add them together, you have parallel trends. Right? And in that condition, the parallel trend is always satisfied, no matter what kind of strictly monotonic transformation you conduct. Okay. All right. So this is a very strong assumption. Why did I discuss this paper? Why do I incorporate this paper in this set of slides? It seems to be irrelevant to the rest of the discussion. I just want to use this paper. First of all, it's a nice paper. And secondly, I want to highlight that you may think parallel trends assumption is weak, but it does not necessarily weak, because in order for it to be reasonable, to be really defendable or defensible, you actually need pretty strong assumptions. Otherwise, you are making a functional form assumption. Okay, you're assuming that any kind of unit level heterogeneity can be differenced out. So you impose some additivity for the outcome, for your version of the outcome.
I'm trying to think about this question backwards, and I wonder if we could use we could just scale our variables and random regressions and use it as a diagnostic test for the parallel trend assumptions. So for example, if we have the data, run a regression and then log transform the data and then do some other transformations, and if the results are inconsistent, then I would say the assumption did not meet, or at least it's not randomly assigned.
You're right, and your proposal is very reasonable and is what I am doing and what most people are doing. But I want to be more precise. First of all, this assumption is not testable, but you can gauge the assumption, the parallel trend assumption, by looking at the pre-periods. And it's just very reasonable things to do. But what I want to highlight here is that when you are making such a judgment call, whether this version of parallel trends is more reasonable than the other version meaning the log or did not log, or what other type of outcome you're using, you're suggesting that the parallel trend is only satisfied with a special version of your outcome, or with right? And because under that outcome, when you use that outcome, your modeling assumption for additivity is satisfied. That is all I want to say. So what I want to say is that parallel trend is mean independence. And in order for that mean independence assumption to hold, you need some assumption for the functional form. Although very often we ignore that, but these are different from the mean independence in experiments. In experiments, you have mean independence. This is guaranteed by randomization. It does not require functional form assumption. But what you have proposed is totally reasonable when you have observational data, when you don't know how the data are generated, and most likely not generated by random assignment. That's perfectly a reasonable thing to do. And one extension to the DID is Semiparametric DiD by Abadi in RES 2005. What he suggested is that the parallel trend assumption may not be satisfied, but after conditioning on some pre-treatment covariates, pre-treatment characteristics, is much more likely to hold. Again, this is also conditional on a particular form of the outcome. So you still have some assumption. So that is called semiparametric. That is why it's called semiparametric, right? It's not non-parametric. Semiparametric DiD requires some parametric assumption, some parametric requirements. The two-step, the first step, you estimate propensity score and then based on some covariates and the computed fit value, and then you run a weighted DID. There are actually different versions of this strategy. You can use this is IPW weighting, inverse propensity score weighting. You can do balancing as well, entropy balancing, covariance balancing, propensity score. These are all in the same spirit. So or you can do even matching. You can match on covariates, pre-treatment covariates, and then using the match pair to conduct the DID. That is all in the same spirit. So this is basically saying, I want to limit my focus to a subset of control that are more similar to the treated in a way. It's not distributionally similar, but at least in the way they change over time. The average potential outcome evolve over time. They're similar, and then by trimming the data, you get closer to the parallel trend assumption. And I think the idea of using pretreatment variables to adjust for the trends is linked to his idea of synthetic control. And of our friends, Anton, extend this approach to incorporate pretreatment outcomes to IPW weighting.